Right, so next speaker is John King from the University of Nottingham. He's going to speak about multi-phase modelling of biological tissue.
So thanks to the organisers. I'd like to single out Mark, who's been patient with me being a nuisance down a number of years. So thank you very much. I'm probably in a minority here, and I'm going to use multi-phase primarily in the sense of mixture theory, not of interfacial dynamics, so there will be an interface in here. I'm not going to get into very concrete stuff. I've actually used this talk to try and organise my thoughts about the mathematical structure of these models, though I don't claim to be anything beyond an amateur in terms of mixture models, so I welcome feedback. The motivation is biology. I'm going to say very little about biology, but I did want to start by emphasising why you'd want to worry about a large number of phases potentially. So if you're growing tissue, so in developmental biology, cells will be going down different differentiation pathways. So you might be worried about a large number of different cell types. If you're doing cancer growth, you'd worry about healthy tissue and malignant tissue. Extracellular matrix, and the equivalent for bacterial biofilms is BPS, is the stuff that sits between the cells and in part holds them together. We are going to be doing tissue growth, so you need to make tissue out of something, and I'm going to make the simplest possible statement about that cells are primarily made of water, and I'm not going to go beyond that in this talk. So I'm going to talk about two different versions of the same model. So this is a version that's commonly used. It's the way I used to think about it. I'll get to the other approach shortly. Even with this, there are a number of variants of it. So simplest possible setup, two phases, both incompressible, no change in volume on phase change. You make cells out of water, so you've got the same sink term in the water equation as source term in the cell equation. Okay, and the two add up to 1 because they're volume fractions. So the top equations are going to hold throughout. The momentum equations underneath are going to appear in different guises later on. So I find this setup appealing in the sense that you naturally separate out the intraphase forces from the interphase ones. So there's two versions, there's two contributions to the interphase part of it. There's the final terms on the right, which are the Darcy-Drag terms. There's the forces each phase exerts on the other, which is those interfacial pressures, the PIs, and then the forces each phase enforces on itself, which is the first terms there. So there's three pressures there, so you don't have a closed system. So to get a closed system, I specify the water pressure, I just call it P, and then take the other two to have extra pressure terms, which I take to depend only on the volume fractions. So all the biology goes into those capital sigmas. So how strongly cells adhere to each other or push each other apart if you try to cram them together, osmotic pressure, so on. Okay, so one naturally starts with one dimension, of course, and if you do that, you can integrate everything up and get a single scalar reaction diffusion equation. So I record how you do that here. With suitable boundary conditions, the sum of the velocities, the volume-weighted net velocity is 0. There's a force balance, which gives the weighted sum of pressures to be 0. So you can express the velocity fields in terms of the pressure gradients, and then from the pressure expression, express the pressures in terms of the volume fractions. So that means you write everything in terms of n, and you get the penultimate equation there, which tells you, unsurprisingly, you've got flow down a concentration gradient. You've got a variety of fixed law with a specific set of nonlinearities arising from the previous slide. Right, so it's maybe worth flagging already that the two key differences from ordinary fluid mechanics, and of course these models are much less generic, which will cause me complications later on. So the two key differences are the fact you've got Darcy as well as Fick. So Darcy for the usual region, and then the capital sigmas give you Fick, and then the source sink terms in the continuity equations. So you get a reaction diffusion equation, but that kind of isn't the end of the story with that, but I'm not going to say any more about it. You can worry about keeping the volume fraction below 1, so that there's assumptions you have to make about it. But people investigate travelling waves. They do the standard things in that setup. Okay, the second approach, and the one I now favour, is variational. So there's this centuries-old debate about where you sit on the spectrum between variational methods reflecting something profound about physics and where they're just a useful mathematical artifact. So I'm going to be agnostic about that, but in effect I'm going to advocate for using them because you get a lot of convenient results out of the variational statements. So the variational part has two distinct components. The first is the free energy. Here I'm just going to take it to be a function only of the volume fractions. More generally, you might want to penalise interfaces and put in gradients as well. So that will be implicit. So I've written down what in other contexts would be chemical potentials here as variational derivatives. In the special case I'm going to talk about, they're just partial derivatives. So the Rayleigh approach tells you to take the time derivative of the free energy and then add a dissipation term. Okay, so I've recorded what you get from the time derivative of the free energy. So I've got an evolving domain, so that's the tissue domain, so it will depend on time, and I'm going to worry a bit about the boundary contributions when I do that. So that's the bulk term. You substitute from the continuity equations and you get this set of contributions. There's the surface term again. And then Rayleigh tells you to add the dissipation function to that time derivative. So there's the viscous dissipation from Darcy drag. I also want to enforce overall incompressibility. So in the usual way, the pressure is a Lagrange multiplier. So the first variational statement involves these variational derivatives. The second involves taking the variational derivative of the Rayleigh with respect to the velocities. And you get these two equations at the bottom. So that they are equivalent to what I started with, and I'll come back to that in a second. Okay, so what does the variational structure tell you? It tells you you're in, I think, pretty good shape. So if you add the two momentum equations together, you get overall conservation of momentum, which Newton would be happy about, I guess. So here in the local case, it's all explicit, but more generally, you appeal to Noether's first theorem, and as long as the free energy is invariant under spatial translations, you get a divergence there, which is what you need. If you derive the energy equation by dotting each of the momentum equations with the relevant velocity field, you do the manipulations, you get the rate of change of free energy, the transport of energy, and then two terms on the right. There's the expected viscous dissipation term, and then there's the energy change from change of phase. So this says that when you convert one volume fraction of water into a volume fraction of cells, you have to spend energy and therefore generate stored energy by doing it. So that's another aspect of biology. If you're just doing rational mechanics, you'd have to make sure that thing was negative. You don't need to do that here because cells can burn energy. There's no metabolism in this kind of model. Okay, so Noether's first applies here as well, but now it needs to be invariant under T translations to get the time derivative plus a divergence. In this, the special case I'm dealing with, you just get the time derivative. There's, of course, one more conservation law, which is angular momentum, which is completely vacuous in this case. For the model is simple, it gives you no extra information, but it better work, and indeed it does much more generally, as long as the free energy is invariant under rotations, as you'd expect. Okay, so I need boundary conditions. We're not doing standard fluid mechanics, so it's not immediate what they are, but that's where the boundary contributions come in. Did I write them all down? I've forgotten. No, I didn't write them all down. So when you do integration by parts on these divergences, you get extra boundary contributions, and you've got the one that's already there from the fact the domain is evolving. So if you apply variational argument to the boundary contributions as well, you get these expressions at the top. So you get pressure in terms of the volume fractions on the boundary, also in terms of the water chemical potential, and by eliminating you get an explicit expression in effect for the density of cells on the free surface. And you can track back and check that that's equivalent to the statement that there's no energy gain or loss actually on the interface, which is something you'd like as well. So I claim the variational argument does tell you the right boundary conditions as well. I'm going to make a number of comments linking the two different approaches. So I need to extract from this version of the model what the intraphase pressures and the interphase pressures are. Now, there's no unique way of doing that. There is one constraint that has to be satisfied, which is to do with the total momentum equation. And that's the one that's recorded there. And the simplest way to share that out between the two different phases is recorded at the bottom. Right, there are circumstances when that's clearly not the right thing to do, but I'm going to stick with it here because it is instructive. So with that sharing out of F between the two phases, you end up with the interfacial pressure taking that form. So what in effect happens is the stress within each phase gets shared out according to the volume density of the other phase in the interfacial pressure, and of the existing phase in the intraphase pressure. Okay, so again, I now do one dimension. So from a couple of slides back, the top equation there, you get the pressure in terms of the Legendre transform of F, which you'd hope, sorry, I'm gone far enough, which you'd hope for from thermodynamics. So in other contexts, you'd view that as a balance between hydrodynamic pressure and osmotic pressure. So that tells you the pressure in terms of the things you actually want to solve for, and then you just plug it back into the other stuff, some of which we've seen before. You get a reaction diffusion equation for exactly the same reason as before. You get a natural driving force, which is the difference in chemical potentials. And if you do the very simplest thing you might think of in this context, take the chemical potentials to be the entropic ones, take the permeability to have a simple dependence on the two volume fractions, which people would often take, you get a linear diffusion operator. So that appeals to me because everything seems to hang together in terms of the simplest setups. Okay, I've only talked about 1D so far. And most of you will probably already notice there's going to be a problem. Right, so that equation at the top is a gradient term. So this is nominally n equations, where n is the dimensionality, but it only involves one variable. And indeed, you can integrate the thing. That variable has to be a constant, and for suitable boundary conditions, it's just 0. So you've gone from n equations to 1. So you've lost a lot of degrees of, a lot of the governing equations, which is what I've recorded here. Okay, so it's not just that one dimension is simpler, and of course you'd always do one dimension first, I guess, unless you're a bit of a potty numerical person. There's a fundamental issue in going to higher dimensions that isn't shared by one dimension or indeed radial symmetry, and that's this here. You don't have enough equations. Again, you can give a mathematical interpretation of that to do with Noether's second theorem, which states that the Euler-Lagrange equations are not independent. If there's a symmetry, there's symmetry that depends on all the dependent variables, and that records what it is in this case. So if you can add on an arbitrary solenoid or field, and it leaves the Rayleigh invariant. That's got n minus 1 degrees of freedom, which is why you've collapsed from n equations to 1. Right, so that means you would go astray if you did the obvious thing, right? There's an obvious higher dimensional generalization of this thing where you replace the x derivative by nablas. So a high dimensional reaction diffusion equation is appealing, and some people do it. But the only way you can get there from this setup is to do something extremely dodgy, which is to go from your overall incompressibility condition to claim that the individual velocity components satisfy, the individual velocities satisfy that constraint, which is relevant in 1D, but is not a deduction from that in higher dimensions. But if you do that, you do get the obvious higher dimensional generalization. Okay, so what do you do instead? The obvious thing to do is to add on a Stokes term as well as a Darcy term. So rather in the spirit of a Brinkman setup, but it is kind of natural in this context because you'd expect the cellular viscosities to be significantly larger than the water viscosity. So in principle, those two sets of terms could balance, but equally you might want to take the limit that those viscosities are small in order to derive a solvability condition, which I'll come to in a second. So I know you've got overall incompressibility, but not each individual phase doesn't have zero divergence of the velocity field. So the bulk viscosity term in general you need to keep as well. So if you want to reinstate the dominant balance involving the first set of terms there, in other words, by taking these small, you need then to get a solvability condition to close this system. And you do it in the obvious way from fluid mechanics, which is you take the overall momentum equation and take the curl to kill the pressure terms. So you're kind of forced to think about vorticity equations here that you might not be, that otherwise you might not be driven to. It's not clear to me that that gives you much extra mileage in terms of analysing those models. So if anyone has any insight into that, please let me know. Right, and one thing I said at the beginning is because these are much less generic models than those in fluid mechanics, you can't immediately transfer information about boundary conditions. I need stress conditions for each phase, and it's not immediately clear what the right one should be. The variational arguments get you quite a long way, but I've still got some questions about that. Okay, so the original setup I gave for two phases involving the intra and interphase pressures, there's no immediate generalization of that to more phases, but the variational approach is immediate. You simply make the free energy depend on each of the volume fractions and go through the same machinery again. So the momentum equations are essentially Maxwell-Stefan, although as far as I can make out from the literature, Maxwell-Stefan doesn't normally have the pressure term, which means because you've got one less variable, you end up having to enforce constraints on the diffusivities, the things equivalent to these kappas. But anyway, these are the momentum equations if you go through that line of reasoning. The interaction terms, of course, have to be symmetric between phases, as Newton would claim. The Onsager reciprocity does sit somewhere in these setups, and I've forgotten where. I didn't have time to check before writing the talk, but that may be where Onsager reciprocity sits. So I think this stuff is probably thermodynamically consistent. So with more phases, you get the same issues as with two phases. So in dimensions higher than 1, this isn't a closed system. You need extra terms. But it isn't actually any worse. It's only the overall momentum equation that's a problem, and there's only one of those. In one dimension or with radial symmetry, you can go through the integrate up. You've got to invert a matrix here to get the velocities in terms of the gradients of chemical potentials. But if you go through all that, you end up with a fairly standard looking system of coupled reaction diffusion equations. I'm nearly done, so I will finish slightly early. So I do want to keep trying. I want to keep trying to understand the relationship between the two different setups. So from here, I want to understand what it looks like if you do think in terms of intra-phase and interphase forces. And again, there's only one constraint you get, and then you have to make some assumptions in terms of splitting it down. So this is the simplest assumption. It corresponds exactly to what I did with two phases. But again, I repeat the point, this isn't always the right thing to do. It's not always the right way to share out the free energy. But if you do that, you get something that looks quite appealing. The pressure terms in the variational setup here, I go through the arithmetic based on this change of variables from P to the intra-phase forces. And the manipulations take you down to this line at the end. So you get, this is what I view as an appropriate generalization of the original setup to higher phases. Here's the force the phase exerts on itself. Here's the force one of the other phases, the J phase, exerts on the I phase. So that's how the J phase force gets shared out. And again, because of Newton's third law, you need to have the corresponding force exerted by the I phase on the J one. So I think that's the interpretation of that set of expressions. Okay, so I am done. Some concluding remarks, partly repeat, but there's one extra thing I want to say that's not on the slide. So I do now think of these things in terms of Rayleighan's, both because they give you shortcuts and because they give you mathematically appealing properties as an automatic consequence. It's not, there are issues beyond ordinary fluid mechanics in understanding what the right setups are, and I repeat the point, there are two sources of that. The simplest is the source sink terms. You're not conserving individual volumes of phases anymore. But more importantly, there's what I keep calling the chemical potential contributions. And again, you can think of that as having Fick as well as Darcy all the time. There are other related formulations I haven't talked about, but the same kind of arguments go through. So one of the most important is a lot of tissue engineering technologies involve growing tissue in vitro in a porous scaffold. So in that case, the dominant drag terms will typically be between the phases and the stationary scaffold. So they look different from the drag terms I had before. And that case is actually simpler, which is oddly the reason I haven't talked about it, because you don't get the paradox about not having enough equations if you do that case. The additional thing I wanted to say, which is not on the slide, is the dominant approach now in math biology to these kind of applications is agent-based models, which use free energies to determine the interactions between individual cells. So my suspicion is if you do want to upscale in this sense to get a mean field model, it's probably relatively easy to read off what F I should be taking to correspond to those agent-based models. How you'd use homogenization to derive the momentum equations and things is probably a much harder task. So those were my concluding remarks. Thank you very much.
Thank you very much, John. Would anyone like to ask a question?
Yes, you can. Yes, I agree in the sense that I like variational approaches as well. Could you say a little bit more about the difficulties with the boundary conditions you had? You said that the variational approach got you so far. Is the issue that you still have to decide how to partition things between the different phases?
So possibly the issue is either my stupidity or I haven't thought hard enough about it, but I think I do largely understand it. So at least the natural boundary conditions you get from the boundary contributions, as I did in the simplest case, almost close the model. There's this slightly odd thing that you want the cellular phases to satisfy a kinematic condition, so that's at the edge of the tissue.
Yeah.
The water doesn't, because the water's got to get in to make the new cells. So the different phases operate in a completely different way, and you've got to concentrate quite hard.
Right, okay.
Any other questions? Okay, I think if not, let's thank John again.